Okay, let's start. So it's a great honor for me to introduce John Robert Brucato, who has been mentoring me since my master's thesis. So I'm very grateful to him because he introduced me in the astrobiology field and he supported me through all my early career. So yeah, let's jump to the formal presentation. He's an astronomer at the National Institute for Astrophysics, in particular the Astrophysical Observatory of Arcetri. He's also a professor of astrobiology at the University of Florence and a member of space scientific boards at the European Space Agency. His main research interest is in laboratory studies related to astrobiology, such as the synthesis of biomolecules in space-simulated conditions and the chemical and physical interactions of biomolecules with dust grains in order to understand basic mechanisms responsible for the origin of life on Earth and possibly on space. Further activity pertains to the study of mineralogical and organic composition of meteorites, interplanetary dust particles, and Wild 2 comet dust sample returned on Earth by NASA's Stardust mission. He is currently involved in NASA's IRIS-REx sample return mission and is a co-I of MoMA instrument on board ExoMars. Beyond his scientific activity, he also carries out technological activity on instrument design, development, and calibration for robotic space missions. Thank you.
Thank you, Teresa, to introduce myself, and thank you all to be here, to invite me here. It's a great pleasure to stay here at the Carnegie Institute. So I'm going to explain some of the results that I made in laboratory, trying to simulate the interaction of molecules with the surface of dust grains, because the dust grains are ubiquitous in the universe, as you well know. So in terms of mass of the galaxy, the 90% of the mass is embedded in the stars, and the rest of 10% is interstellar medium that's made of 99% of gas, and only 1% is of this interstellar medium is in terms of mass stay in the dust. So it's a very small fraction. But the dust, this 1%, is not only the subject of the studies that we have made in last years, but it's also an active, he plays an active role in driving the process that occurs in the star formation, especially because it's going, the main role is to cool down the molecule. I mean I have to switch to the English. I'm sorry. I was just speaking in Italian last time, and so I have to start again. So in the dense molecular environment in which the dust is playing this role in cooling down the clouds. And so, especially when we are talking about the dust grains, so the grains are producing mainly in the envelope of expanding envelope of evolved stars, especially the asymptotic giant branch stars that are the major sources of the dust. So the dust condensed in the envelope is injected in the interstellar medium, and so they made a cycle between the dense and the diffuse interstellar medium, and it was estimated that before it will be ended up in the formation of a new planetary system, at least 10, 20 times single dust grain is cycling between the dense and the diffuse interstellar medium, in which we have a different temperature and different density of the hydrogen, especially, is the way in which we define the diffuse and the dense interstellar medium is is thanks to the fact that the diffuse interstellar medium has one particle of hydrogen atom per cubic centimeter, and in that case we have up to 10 to the 6 at 10 to the 8 hydrogen atoms and also molecules, because the temperature is very low, that's per cubic centimeter. So in the dense interstellar medium, we have the possibility to produce a new planetary system, and new stars are formed. A fraction of the matter that is present in the dense interstellar medium is condensing, producing the planetary system. And when the star masses are around a few solar masses, we have a planetary system. If the mass of the star is larger than that number, so we have a large, very heavy star formation without the presence of any planetary system that will end up with the formation of a supernovae. The stars that are involved in the formation of a planetary system usually will end their life producing again the AGB or novae stars. So, and again, the cycle is continuing. So we have some information of the presence of the minerals and dust grains in space. Here is I would say, a quite old spectra in the infrared of an evolved AGB stars, in which we can see in the infrared, this is the infrared spectrum from a few microns up to 50 microns. And so we can see the peaks, a very sharp spectrum, in which we have a lot of bands that testify the presence of crystalline silicates. So it's a fraction of the dust that is condensing in the envelope of evolved stars is producing crystalline, in particularly olivine, in that case, silicates. When we move from the envelope of evolved stars towards the interstellar medium, so we have that the band of the silicates of the dust are smooth. So we have not, we haven't seen any of these very peaked bands in the interstellar medium. So the fraction of the crystalline material that has been detected in the interstellar medium is just a few %. So that, what does it mean? It means that probably or the fraction of crystalline is too low that is produced in the envelope of evolved stars injected in the interstellar medium, and so it's diluted in that environment, so to have no signal in the infrared, or there is some processes that amorphize the crystalline silicates when they are going in the very dense, or diffuse environment like the interstellar medium. And those processes could be the ion radiation, because we have seen that the ion radiation is very effective in amorphizing the crystalline silicates. So when we go to the solar system, there are hints that testify that, again, in the comets, in this case, this is L-Bob comets, so we have the presence, again, of intense peaks that demonstrate the presence of a fraction of crystalline material, and again, here we have the forsterite. Also, we have the CH band at 3.4 micron that is the presence of this band is demonstrating that some aliphatic hydrogenated amorphous carbon, we call them, are present in the interstellar medium. So there are a lot of information that we get by remote sensing, but we also can had the demonstration for the first time of the presence of crystalline material. Especially, I will focus on that aspect in the grains returned by stardust of Wild 2 comets. So here is some example of a Fosterite. So it was showed that a sort of continuum there is evidence that support the idea that there is a continuum between asteroids and comets. So in that respect, a fraction of 10% possibly of the cometary grains are made of crystalline grains. So that was really a surprise because, as you know, so we have the condensation of the comets in the outer part of the solar system where we have the condition in which the temperature is very low, and so if the fraction of crystalline is so low in the interstellar medium, so we have to introduce another way to produce and deliver those grains in the site where the comets are formed, and especially it's coming from the inner part of our solar system. Another model that has been made in which we can have the different expectation in terms of fraction of silicates, crystalline and amorphous, according to the distance from the sun in our or other planetary environment, planetary systems. And so we have that going in the region where comets are coming. So we have that a very small fraction of crystalline material can be found. Instead, when we go in the near part of the solar system, we have a really high fraction because the temperature is very high. And so we have a high fraction of crystalline material. So we can now talk about a sort of mineralogy of the interstellar medium. In this case, so we have, this is an incomplete inventory, so just to have a picture of what has been found in space in terms of the composition of the dust. So we have oxide, carbide, carbon-based material, sulfide, silicates, carbonates. Okay, so another picture that is showing a model, a cartoon in which we have in the path that the grains with the molecules that are condensing on the surface of the grains are doing in terms of processing, in terms of chemical composition changes starting from the interstellar medium when a nebula is collapsing, forming a new protoplanetary disk. And so we have the grain, it's covered by water-rich mantle, icy mantle. So when the density is going up, so we have also more volatile species condensing, and so we have also a fractionation of the ices on the top of the grains, and so moving down where the temperature is going up, so we have that the processing, thermal processing occurs, and so we have that the formation of a new second generation of molecules occurs, and in these cases, so the radicals, methanols are formed as a main molecules, and we have that the complex organics are produced when again the distance of the grain is lower from the central stars, and when they are again inside the disk, another condensation of volatile species occurred, and at the very high temperature, all those organics are sublimated by the radiation of the central stars, and the more refractory grains survive. So all the story that you really know. So now I'm just talking about the role of the minerals, because the minerals can accumulate prebiotic precursors. So this is one of the aspects that are really interesting in our cases in order to try to find the presence of organics in different space environments. The dust can act as a catalyst, so they can reduce the activation energy in producing a new species, new chemical species, can tune the selectivity of some prebiotic process, some prebiotic synthesis, is also they can act as a template. So the absorption of molecules can occur in a very specific geometry that can favor the production of some kind of molecules when they made a link together on the surface of the dust. And dust could preserve newly formed biomolecules. This is my outline of the outline of my talk. So the central role of the dust in doing some processes that involve the gas, so neutral atoms interacting with the surface of the dust, molecular lysis, so solid can interact with the dust, and liquid, so some molecular solvents, organic solvents, can how they interact with the dust. So I will go through those three aspects. So that's a picture of what we have done in the last decades, I would say, but I will concentrate on more recent results. Some of them are, of those experiments, are done by using synthetic silicates. Especially in this case, we have olivine and pyroxene that are produced by two different techniques. This is the laser ablation, and this is the electron beam deposition, in which we can have different shapes and morphology of the amorphous grains. With those techniques, we produce amorphous silicates. In this case, we have a very fluffy grains that are mainly made of those spherical silicates, amorphous silicates, with the main size of 10, 20 nanometer. With electron beam, so we can have the same composition, the same stoichiometry, but with a very flat shape. So that's really interesting when we want to study the interaction of the molecules with the surface of those minerals. I mean, we can also anneal these grains, this sample, and producing a crystalline material with the same composition. So we can also tune the stoichiometry in order to have a different kind of composition. But we also use natural minerals, so terrestrial analogs, in order to perform our experiment in the lab. So I'm going to this interaction of natural atoms with the surface of the minerals. As you know, molecules in the interstellar medium, this is a quite recent list that has been found in the, are around 200 molecules. They are called complex organic molecules, even if for, astrobiology perspective, they are not so complex, but in any case, there are also some biasing in detecting those molecules by radio astronomy is due to the fact that they have a permanent dipole moment. So it means that the other kind of molecules without any permanent moment of dipole is not detected. Anyway, so they are increasing a lot, the list, and so it's nice to see if we can reproduce in the lab, so try to understand the chemical path that is followed in space in order to produce some of those molecules. So there are many theories, many processes that can produce complex molecules in space. So here there are some examples: the gas phase ion molecule interaction, low temperature gas grain reaction, photodissociation, photopyrolysis, so isotopic substitution, and so on. So we can explore some of those kind of processes in the lab, and especially we have studied two very famous interactions that can occur at very low temperature when natural atoms are colliding at the surface of the grains and are sticking on the grains, and they will interact with another natural atoms that is colliding and react. In this case, the theory is made by Healy-Riddle, in which we have a very high coverage of the surface of the grains, in which a new atom colliding will find surely another atom on the surface reacting, and when the temperature is high enough, it would be desorbed in the gas phases. So many of the molecules that have been observed in the gas phase, we postulated that they are formed on the surface of the grains, even if there are some other people that believe that those molecules will be formed in the gas phase. So the other process is Langmuir-Hinshelwood, in which we have the absorption, the diffusion on the surface until the atom will found another one, interact, and desorbed again. What we have studied is the water ice formation and on the surface of amorphous olivine. And so there are three chemical paths that has been supposed to be active in space, and especially the reaction of hydrogen with the molecular oxygen that will end up with the reaction of other atoms with the formation of the water ice. This was introduced and postulated by the Ioppolo, and the other one by Thiele and Hagen is the role of ozone in the production of the water ice, again interacting with the atomic and molecular hydrogen, and the other one is the direct formation of molecules of water ice by reacting hydrogen with oxygen. The main problem is that when you produce a new species on the top of the grains, the energies could be so high that they will desorb immediately. So in producing some of the intermediates, you will not end up in the formation of the water until you dissipate the energy that is doing by the atom that is coming and reacting. So we have made some experiment in which we bombard the surface of amorphous olivine with hydrogen, deuterium, and oxygen. And this is a temperature-programmed desorption experiment in which we have the increasing of the temperature of the sample in a linear way. So we have at the sublimation temperature that the species are desorbed, and so we can detect with mass spec. So we have that the formation of HDO, D2O, and so on, and deuterium peroxide, and so, and also the formation of oxone happens just by bombarding with the atoms the surface of the grain. So we also made a formation of water ice, and we detected by Rayer spectra. So it's an infrared spectrum of the water ice synthesized on the top of the grains. So we can detect the energy of the binding energy of those species, and so we can also measure the formation efficiency, and so we can have a different temperature. So we have that the efficiency is really very high at temperature that are found in the dense medium, in the dense cloud, and so we have the formation of DH2O and D2O2 is very high. So we can conclude that the formation of the water follow the hydrogenation of oxygen, of the oxygen. Okay, so going to the molecular catalysis, so we have that different environments I've found in space. And so especially we have that the ion are releasing very high doses according to the environment in which we are looking for. And so also the photon processing is also very important in different environments that could be the diffuse dense or protoplanet nebula and so on. And in the lab, as you can see, we have a very few time. That's the lifetime of the researcher that can reproduce a very small fraction of the process that can occur in space, obviously. And so we try to find the very basic parameter that drive those processes in order to exactly simulate what in terms of energy those are expected in space. So especially we have focused our attention on formamide. Formamide is very promising molecules. It's a very simple carbon-bearing molecules, one carbon, one nitrogen, one oxygen. And it's formed by hydrolysis of ACN. It's very active in the synthesis of nucleobases and was also observed in different environments. So this formamide is very, very interesting. So there are different kind of models that describe the formation of formamide that could be on the surface of grains, in the gas phase, and so on. So here we have some experiments in which we have the irradiation, ion irradiation of pure formamide. You can see that in these cases, the pure formamide is in the infrared spectrum has a very intense bands. And so we have the formation of these new species, new fragments, when we irradiate with the 200 keV of protons. And here there are some zoom of the spectrum in which we have the signal of the fragments that has been produced. Especially we have also irradiated recently the formamide when it's mixed with the CO, water ice, or when it's pure. And we have in a different temperature, so we can have that the different paths are followed when we irradiate those species in different kind of mixture. Especially, so we have that when we irradiate at the very low temperature, at 20 Kelvin, the formamide, it's volatile in the sense that at the vacuum, in the vacuum chamber, so in the vacuum system, when we increase, so we put up the temperature, so it's completely sublimated. But after the irradiation, we have that ammonium cyanide is found at room temperature. So there are the band testify the presence of ammonium cyanide at the room temperature. So it means that irradiation, the processing of ion irradiation of some ices like the formamide can produce a refractory, more refractory species that can survive at high temperature. Here we have irradiated the formamide, pure, and this is the pure formamide, and the blue one is when it's deposited on amorphous olivine. And so we can see that some of the fragments that like NH4 or HCN are not formed when the formamide is in contact with the amorphous olivine. So in these cases, instead to increase the complexity of the new species that are formed after the ion irradiation, so the silicates prevent the formation of some of them. So the minerals can also have a pivotal role in the evolution of prebiotic species because they can mediate the effect of the ion and the photon irradiation, influence the photostability of the biomolecules, catalyze some specific chemical reaction, and protect the molecules. So we have studied the interaction of more complex molecules that has not been detected, in space up to now. So, but it's, the promising path for the future development of new kind of instrument that will we hope that we can be able to detect such kind of molecules in space. And so we have studies the interaction of different kind of biomolecules, and especially we have the nucleobases, nucleoside, nucleotide, amino acids, some pHs and formamide with a different type of minerals. So those are the experiments that we have done. So we have in plan a very quite high activity and complex, study in order to understand the interaction of all of these species with the minerals. So we are ongoing. It's a process that is ongoing. Here some special hints on formamide interacting with silica, alumina, zeolite, kaolin, carbonaceous calcium carbonates, and titanium dioxide, and morillonites. What is produced? In this case, it's a liquid, it's a terrestrial environment, or a planetary environment in which we can have the liquid of formamide in liquid form state. So we have the formation of a lot of purines and pyrimidines. So it's a really very exciting and promising molecules because it's possible to synthesize the building blocks of life. So we also found a specificity in the formation of some of the species. So in this case, we have cytosine. It's written in Italian, sorry. So we have a phyolite here. So when this is the efficiency, the yield of cytosine when we have pure iron olivine and compare with the efficiency that's is 0 when we have magnesium. So the role of the iron in the olivine in synthesizing those species is relevant. So there is some specificity in producing the nucleobases. We have irradiated with UV formamide interacting with the anatase and rutile. So there is a different gap, energy gap. So they are photocatalysis, as you know. So we can have photochemistry in these cases. And so we, instead to synthesize nucleobases, we have produced carboxylic acids by irradiating with UV the titanium dioxide. Those are the yield that we have obtained. As you can recognize, they are 6 of the main molecules that are found in the carboxylic, so the Krebs citric acid cycles, Krebs cycle. So it should be a path that in a prebiotic environment can be found in order to have all the ingredients, all the molecules that have been active in the formation of one of the best, I would say, metabolic cycle that could also work in the reverse direction in as was supposed in the prebiotic environment. Absorbing nucleobases on minerals. In these cases, we have an example just to show you. It's very time-consuming process that is describing the way in which the nucleobases can interact with the surface of some of those minerals. Specifically, in these cases, we have the magnesium oxide, and so we have that the adenine, for example, is absorbing well than cytosine. So we have more chance to have adenine in contact with with the magnesium oxide with respect to the cytosine. And here we have compared the absorption process on brucites of uracil, uridine, and uracil monophosphate. And so we can see that the presence of phosphate is really important in the interaction. So because it's a very high yield of the absorbing process when we have the phosphate in the biomolecules. So it's really interesting. Also, we have the interaction of is a chemi-desorption in the case of the uridine monophosphate, and so we have also that the biomolecules can self-organize. This is a tridentate, bidentate, and monodentate interaction with the surface of the grains, and so we have that this absorption can drive the self-organization of those molecules that could increase the complexity of the species when interact on the surface of the minerals. So we have also irradiated by UV. And here we have, I don't know if it works or not, probably not. Let me see. No, okay. It's just to show you, where is, okay. This is the uracil with a UV radiation, so you can see the photodegradation. It's it's a movie just to show you how all the chemical bonds are broken. I mean, and so we can measure the degradation of the uracil. We can derive some important parameter, that is the cross-section of degradation of the biomolecules with which you can model how those molecules can be degraded in different space environments, just changing the environmental condition. And so we can have that the cytosine epoxanthine have a greater photostability, and the adenine and uracil degradation was very fast. I mean, and so the presence of the minerals, instead to protect the biomolecules, the nucleobases, they act as increasing speed up the degradation. So it's not a protecting aspect. So we have here the time that we have derived for the photodegradation of the nucleobases. So adenine and uracil, in these cases, we have that some few hours can be, and this is a Martian condition, so we can have a few hours, they will survive when exposed to the Martian environment, to the surface of Mars. So if we will drill and collect. So new species are also formed after the UV radiation, and especially the cyclobutane dimer are found, though this means that we have a geometrical arrangement of the molecules on the surface that can promote the formation of those kind of species. So another kind of interaction is here we have naphthalene and naphthol, 1,8-dihydroxy naphthalene and 1,6-dihydroxy naphthalene. Here we have the pure molecules, and when is adsorbed on anatase, so titanium dioxide and phosphorite, and again is irradiated for a few hours. So you can see the degradation it's occurred, and as you can infer by comparing, is very fast or is speeded up when when the molecules is in contact with the grain. So again, we can derive the cross-section of those molecules, and so we can estimate the time that they can survive in a space environment. So so we have found also that together with the photodegradation, we have also photodesorption that occurs. So in those cases, yeah, it's a precursor of melanin. And so we have just trying to figure out if some process, some prebiotic process will end up with the formation of those kind of species. So, yeah. I mean, it's... In these cases, we just try to understand which is the chemical situation that we can find in some specific condition. So it's just one example of that we have studied. Surely there are many other way to approach the problem. So, and especially we have found that in the case of dihydroxyl naphthalene, we have that the more stronger interaction has been found. So the oxidryl is a very important mechanism. So molecules, I would say, branches that can I mean, induce a stronger interaction with the surface of the grains. So it's an important aspect that to take into account. Okay, I'm going to the end of my talk. So here we have the irradiation of amino acids. Arginine and leucine is studied. Again, we can infer the cross-section of photodegradation. And especially we can have the lifetime, it's of the order of a few minutes. So in this case, it's glutamic acid, leucine, arginine, and so on. So we have that they survive in space environment very few times. So it's easily degraded. And especially when we compare, in the case of glycine, that's a cool molecule that many has tried to find in space. It's very simple. It's the simplest amino acid. So we have that the time in laboratory condition is of the order of an hour, the photodegradation, so the half times. When we move in the space condition, so they are reduced to seconds. So it means that a few tenths of seconds. So it means that in space condition, they are degraded really faster than in laboratory one. So I'm finishing so by give you the summary. So what we have found is that adenine uracil are fragile. Very fragile. The changes in photophysical behavior of nucleobases are highly dependent on the specific interaction with the mineral surface. So we are trying to derive some general aspects according to the mineral composition in driving these photo processing of nucleobases. The cross-section also that we have found and derived in the lab was exactly, I mean, very similar to what has been obtained by Biopan 6 experiment, in which was exposed in space the adenine. So the irradiation of naphthalene is induce a specific photodegradation. And we have some suggestion of the formation of some polymeric species, but we have are going to study in more detail these aspects. So amino acids are photodegraded faster in space simulated condition. Foster the hematite, MgO, titanium dioxide, nanthrolite, labradorized minerals have no protective effects against UV radiation. Instead, they can speed up, increase the degradation kinetics. And serpentines, minerals, and the apatite are photoprotector, we found. And so there are some physisorption processes. So predominantly, mainly the process of interaction is the physisorption, and the hydroxyl plays a role in this physisorption process. Also, from the perspective of who is studying the infrared spectroscopy in order as a way to detect molecules in space, we have found a shift of vibrational frequencies when the biomolecules is interacting with the minerals, and also the band assignment based on the gas phase model could be misleading in these cases. So we have also to take into account those kind of aspects, because it's very, very important in order to have the right assignment of the functional groups when we are looking at the infrared spectroscopy. So I would like to thank the students and the collaborator, Teresa here, and Giovanni, my student, Giovanni Poggiali, PhD student, Simone Potenti of Scuola Normale Superiore, and the Italian Space Agency to have found this kind of work. So, and all you, I thank you for your attention, and in dust we trust.
Okay, good. Are there any questions, comments, curiosities?
So I was curious, for your very low temperature reactions, how important is it really the chemistry of the sample, or is it just they need a surface?
I mean, in some cases, you don't need the surface in order to have those kind of reactions. So you can have the reaction even with the pure molecules. There are decades of studies that have been made in order to understand what's happened when the biomolecules or very simple icy molecules molecular ices are irradiated in space-like condition. And so there are many effects, surely. So you made radicals, you break bonds. But now I think it's really interesting to have this combination of the dust, so minerals, in order to compare the two things. And as I try to show you, so there are some cases in which they are favoring the degradation. So it's consider that you have a very monolayer of, I didn't talk about that, so you have just a few monolayer of molecules that are interacting on the surface of the grain, even in space. And so in that case, the rule of the grain, of the surface of the grain, is very, very important. So it's an interesting, I would say, I hope, field in which we can have more hints in terms of survivability, in terms of prebiotic mechanism that can be found in space or in the early Earth somewhere, in order to drive more complex chemistry on the Earth or in space.
One other one. I thought glycine has been detected in molecular clouds.
It's tentative. I mean, tentative. All the time they say tentative. I mean, it's really. I mean, it's challenging. We saw that the glycine is very fast degraded, so probably this could be a way why. I mean, we don't see the glycine in space, or I mean, we can try to find in some sample returned material in which the molecules is protected by those kind of energetic processes that can affect the abundance of the molecules.
I have two questions. The first is sort of a follow-on to that, but I was curious about the role of the porous surfaces versus the smooth surfaces in both the formation and the degradation.
I mean, the way in which we have just seen that in terms of efficiency, because we have a larger surface in the case of a porous one. We have not really went into deep detail according to the, how can I say, the effect of pores or the size of the irregularities on the fluffy grains with respect to the flat one. So we have just seen that the efficiency is higher because the surface is larger. So was what we have made, but certainly is an interesting aspect to be investigated.
And my second question about the degradation was just when you degrade, do you degrade all the way down to individual atoms that are then released, or is there some molecule that you build up as a result of the degradation?
Yeah, you break the bonds according to the infrared. For example, spectroscopy is a very powerful way, or also Raman, in order to see which kind of chemical bonds you are breaking. So you can release also very atoms, I would say, very simple species, or you can release in the gas phase the branches of molecules. So. Yes, the carbon is remain. So you can start with a very volatile species, molecular species, carbon-bearing molecules, but you lose predominantly how can I say, the volatiles, so hydrogen, oxygen, nitrogen also, but the carbon will end up as a sort of a black polymeric material that can contain inside some aliphatic aromatic, obviously, molecules, nitrogen embedded in. But so you change the structure for a very, very volatile and simple ISIS to a refractory material. So that's the reason why, for example, in Rosetta, you have this very black surface of the comet that is mainly made of carbon. So I would say it's so black that we never reproduced in the lab blacker than the black, I mean, that we have found.
Any idea about self-shielding? Because you're using a lot of single layer monolayers.
Yeah, surely the clay will play a really, I mean, as well known. I mean, but we already again have found the same result. So they can protect a lot because they between the sheets of the minerals, the molecules are going inside. So they are really a good way to protect the molecules. So it's an important aspect that can be taken into account in these cases because for the UV first layer of molecules, whatever it is, will block the UV, so they will not go inside and penetrate in deep. The cosmic ray, in that case, you have a very large penetration depth of the order of the meters, and so they cross. But if the ions are very energetic, as a cosmic ray, they will cross exciting, ionizing, but not really destroying the molecules. When they will end up when they go to the rest, in that case, there are the largest release of energy displacing atoms. So they amorphize, they break the bonds, and so they destroy the molecules. So the clay are still the best way to protect.
And I probably missed, you probably said it, but I missed it. All these reactions must be wavelength sensitive. So what, are you using a single wavelength?
No.
Or a spectrum line out or something like
Yeah, I didn't say that. So I use a lamp with a broad spectrum wavelength. It's a xenon lamp, UV enhanced xenon lamp. So it's not just to select a range, but it's a broad range of UV. Start from UV up to visible light radiation. That's a really a good question. I have no the answer because there could be some experiment in which they have tried to synthesize the glycine just starting from simple ISIS. And I have no idea of the equilibrium, so which is the fraction, the energy of the time that you have to spend in order to have this kind of information. But there are some information that can be found in the literature that can help in that sense.
But what they should try to do is to reform products of the degradation.
Yeah.
If it's ripping them apart,
yeah.
there, you put them back together.
Yeah, surely. That's, yeah, that's another way to see the things. Yeah.
If there are no questions, thanks again to John.
Thank you.